think we can get started. So yesterday, I was stuck here trying to figure out what the mistake was in computing the covariance of this mean estimator. Right, so for a bunch of samples drawn in an IID fashion from this Gaussian with unknown mean vector mu and known covariance matrix sigma, we derived the maximum likelihood estimator for the mean parameter, which turned out to be the sample average. We looked at the expected value of the sample average estimator, which turned out to be equal to the true value mu that gave us these samples. Right, so we call this an unbiased estimator because on average the estimator gives the correct value. And for the covariance, actually in the notes, in the solutions of the practice questions, I had this first line as the derivation. So covariance of mu hat is, if you plug in this expression here for mu hat, covariance of this scale times sum. Because covariance has a squaring operation, when you're taking the multiplicative factor outside, you need to square it, right? So that's covariance of 1 over n times whatever will be 1 over n squared times covariance of the sum. And then I can switch the order of covariance and summation. Covariance of each sample is sigma, so we get 1 over n sigma. Yesterday I was trying to solve it directly from the expression for covariance, right? So expected value of this random quantity minus its expected value, which is mu, and the transpose of that expression here. So when I expanded this multiplication of sums, we have this 1 over n squared and a double summation. So the mistake I had was I plugged in sigma for this expected value, xi, expected value of xi minus mu, xj minus mu transpose. So I plugged in sigma for all of these, but that's not correct. Actually, that's only sigma equal to sigma if I and j are equal. And if they're different, then because xi and xj are independent random variables, they're also uncorrelated, which means expected value of a product of these two random variables will be product of expected values. And that's going to be expected value of xi minus mu times expected value of xj minus mu transpose. And both of those are 0. So when I and j are different, this term is 0, which means in this double summation, the only non-zero terms occur when I is equal to j. So I can reduce this to a single summation, let's say over index I, and in that case the value is sigma. Right? So that again gives me sigma over n. So you could do this either way. And my mistake here was that I was setting this to sigma, and that's not correct. It should be sigma times Kronecker delta of ij. Right, so only sigma when I and j are equal, 0 otherwise. Another mistake that somebody pointed out after class was for the case where we were estimating the mean with a prior. So we did this derivation for the map estimate, and I was wondering, looking at the expression, didn't tell you. I think I had something like this. So I was wondering why I have a negative sign here, which creates a potentially dangerous situation of having a 0 eigenvalue due to this subtraction, or negative one, which shouldn't happen. So that was a mistake I forgot. When multiplying with -2 in one step, I forgot to multiply one of the terms with the negative sign, and that brought this negative mistake. So if you catch these types of mistakes, let me know on the fly so we can fix it immediately. It also helps me know that you're actually following all these details, so that's good to know. So today the plan is as follows. We have been focusing on Gaussian distributions yesterday to illustrate maximum likelihood and map parameter estimation concepts. So just to have a change, today we'll look at Poisson. Okay. So we'll look at Poisson distribution parameter estimation. Okay, so we'll look at estimating the mean parameter for the Poisson using maximum likelihood and map. And when we use map estimation, we will use gamma prior. And okay, gamma prior happens to be a conjugate prior for lambda. Make sure this is on so we can check it out later. Okay. We'll look at the internet to see what the expressions are for these, so that I don't make a mistake. Okay, so we'll look at these two cases for Poisson distributions. Poisson distribution generates integer valued random numbers. So it's good to have this kind of variation between continuous valued random vectors and discrete valued random variables. You'll see the principle is the same. Then we will look at least squares, model fitting. Okay, so least squares model fitting, or you might want to call it regression, as most people do. So least squares curve fitting, model fitting, or regression as ML or map parameter estimation. Right, so we look at how least squares optimization ends up being ML when you assume additive Gaussian noise. We'll also put a prior on the parameters of the model. We'll choose a Gaussian prior, and we'll get a L2 penalty regularization term, as they call it. Yeah, so we'll do this for linear models first. Then we'll generalize to linear in parameters type models. So these will be, sometimes in statistics people call these generalized linear models. So they're essentially nonlinear functions which have derivatives that are linear with respect to the parameters. And if there's time, we'll just talk about nonlinear models in general. Okay, so let's start with Poisson. Okay, so I have, again, like in the take-home assignment that you have, I have n integers drawn in an IID fashion from some unknown, well, from some Poisson distribution with an unknown parameter lambda. Right, so the distribution of Poisson PDF is, so this is the probability that, let's say the random variable is k, right? So k is drawn from Poisson lambda. The probability that k, capital K, which is the random variable, takes a particular value, small k, right, is, we'll call this pk, is equal to, so 0 if that value is negative, so this will not produce negative integers. And for non-negative integers, the probability of getting that value is just lambda to power k. If I remember, this is the expression, right? E to the power negative lambda, lambda to power k. No, it didn't work. Okay, so so let's first try to get the maximum likelihood estimator for lambda. And just as a side note, if you recall, both expected value and variance of this PDF is equal to lambda. So since expected value of this random variable is lambda, you might have the anticipation that the maximum likelihood estimate will end up being the sample average, like in the Gaussian case, and that will be the case. Right? So let's derive it. So my maximum likelihood estimate will maximize will be the lambda value, which makes this data set as likely as possible. So it's going to maximize this joint probability of observing all those values. Right? And we can call this probability because these are integers, so that's a discrete random vector or random variable itself, right? So these are actual probabilities, not just likelihoods in the general sense. So I can take the logarithm of this so that when I break this down using independence into a product, it becomes sum of log individual. Right? So this is a argmax log product. Right? So that's the joint likelihood of all these values if the correct parameter is lambda. And log of product is sum of logs. Right, so we can equivalently solve this optimization problem. There is a constraint for this parameter because these k values are always non-negative. Their expected value must also be non-negative. Right? So we cannot have a negative value for lambda. It wouldn't be a legitimate Poisson. So the constraint here is lambda must be greater than or equal to 0, actually. So 0 is allowed. I think I mean, if you take what value of lambda would make the expected value? If lambda is 0, yeah, you would just have 1 for 0. So I think technically this is allowed, but if you set lambda equals 0, then that's not a very interesting random variable, right? It's always going to give you 0. So we have an inequality constraint for the parameter that we're trying to optimize here. So this is actually a constrained optimization problem. Okay. And so I want to use this opportunity to talk about constrained optimization problems for 1 second. Let me get my laptop too in case it's faster. So we'll take a sidebar here. This is just too complicated. Okay, just use my own notes. Okay. Okay, so we talked about unconstrained optimization earlier in some detail. But I skipped constrained optimization in PCA derivation. And earlier you saw this concept of a Lagrangian, which comes up when you have a constraint optimization problem. So let's now look at it in a slightly more detailed fashion. So I'm going to try to find here what page the KKT conditions are. Gradient. This looks like these squares. Okay. Okay, here. So we'll come back to this shortly. I just want to remind you first what we mentioned for unconstrained optimization, and then we'll look at constrained optimization. Okay, so if you have an unconstrained optimization problem, right, so I'm trying to minimize some function of x, which is twice continuously differentiable. I assume f is twice continuously differentiable, so its gradient and its Hessian matrix are all continuous, all consisting of continuous functions of x. Since there are no constraints, basically I'm saying x can take any value in this n-dimensional vector space Rn. So the entire space of x is allowed, and a local minimizer of f without any constraints satisfies two conditions, right? So the first order condition is at a local minimizer. Let's say x star is a local minimizer. So if x star is a local minimizer, the first order condition says the gradient must be equal to 0, right? So we use this to solve these minimized quadratic function of parameters type problems. When the function f is quadratic, you take the gradient, it becomes a linear system of equations. You equate to 0, solve for the roots of the linear system, and there will be only one, hopefully, right? And if the linear system is full rank, then you'll have a solution for x star. So if this is a function that looks upwards, so there's a local minimizer, and if it's quadratic, this is sufficient to find that minimizer, right? But in general, there might be multiple locations where a gradient of f becomes 0, right? So you might have a local minimum, you might have a saddle point, or a local maximum. So you need to check also the second order conditions to make sure that the point you found where the gradient is 0 is a local minimum, not a saddle or maximum. So second order conditions state that you should check the Hessian matrix. Just gonna draw that. So the Hessian of f evaluated at this point where the gradient is 0 should be positive semi-definite. If the Hessian has a 0 eigenvalue, what that means is locally at x star, along the direction of the corresponding eigenvector for that 0 eigenvalue, the function is flat, right? Up to a second order approximation. Think about x cubed, for example. X cubed has a 0 second derivative at 0. So if you're standing at 0 and just looking at a quadratic approximation, it looks like a flat 0, although it's not actually, right? Because you have to go to the third order derivative to start seeing that curvature. So if the Hessian has a 0 eigenvalue at x star, then that local minimum could be part of many local minima lined up along that eigenvector of the 0 eigenvector, right? If the Hessian is strictly positive definite, all the eigenvalues are greater than 0, then that x star is an isolated local minimizer, right? So because if you move in any direction, quadratically the function will go up. So you cannot stay at the same value, which is the smallest possible in that vicinity. So this is a single point that's a local minimizer. As soon as you move away in any direction, the function goes up, and you're not at a local minimizer anymore. So you're used to thinking about gradient being equal to 0, right? So now we're going to generalize these two conditions to KKT conditions for the first one, and then some extended version of this second one using the Lagrangian when you have constraints. Right? So let me just go back to this thing here. Most importantly, I would like to emphasize these KKT conditions. Okay. What happened here? Okay. So the problem we are trying to solve is now in this form. I hope you can see this. So I'm going to minimize f with respect to x, but now x is not allowed to take any value. It needs to satisfy these constraints, right? So I have potentially some set of equality constraints. That's the first group of constraints above. So I might have something like ax equals b for some matrix A and some vector b, right? So which means x must lie on a linear hyperplane. That's a subspace of Rn. Not, or I could have a nonlinear equality constraint like x transpose x equals 1, like we had in PCA, right? So which means x must lie on a sphere with radius 1. Inequality constraints are also possible. So for example, if you want to specify x, restrict x to be inside a unit sphere, then you could have an inequality constraint like x transpose x is less than or equal to 1. Right? So now x must satisfy the inequality, which means it has to be inside that unit sphere. If you're outside, that x is not allowed. So we call those infeasible if you're outside the set of values that satisfy all the constraints. Those are called infeasible x values. And if you satisfy all the constraints with an x, that x is called a feasible value. So sometimes people will write here x element of some feasible set f, and then we'll specify f as all the x values that satisfy these. So if you have a combination of equality and inequality constraints indexed somehow, the first order approximation of both f and those constraint functions lead to the KKT conditions as a replacement for this gradient equals 0 condition. So now it should be around here. Okay, so these are first order necessary conditions, right? So for a constrained optimization problem, a point x star must satisfy these KKT conditions in order to be considered as a potential local minimizer. But of course, similar to this case, just satisfying the first order conditions does not make a point a local minimizer. It could still be a saddle or maximum type point. And the second order conditions will split those into these points into those three categories. So let's look at the KKT conditions. Okay, so suppose x star is a local solution of this constraint problem, which means it's a local minimizer satisfying all the constraints and achieving smallest value of f in the neighborhood. Then there exists some vector lambda star, which we call the Lagrange multiplier vector for solution x star. Right, so we have a pair x star lambda star. And those x star lambda star vectors must satisfy all these 5 conditions. And the collection of these conditions for all the constraints and the Lagrangian is called the Karish-Kuhn-Tucker conditions. Okay, so the Lagrangian gradient with respect to x must be equal to 0. Right, so this is the condition that's similar to gradient equals 0. But now we're looking at the Lagrangian, and Lagrangian is, just to make sure everybody remembers, so the Lagrangian is here. Right, so it's your objective f minus linear combination of lambda I, ci, x for every constraint you have in your constraint set. Okay, so each constraint gets assigned a Lagrange multiplier, and we subtract those from the objective. In some books, some papers, people put a positive sign here, and you can see that at the optimal solution, that's going to cause the lambdas to be flipped in sign relative to this definition. So this particular book uses a negative sign here because if you look at the sensitivity of the objective at the optimal, at a local minimizer x star, the value of lambda turns out to be the derivative of objective value f relative to the location of the inequality constraint or equality constraint. So basically the magnitude of lambda is a measure of how the value of f could go down or up if you move the constraint one way or the other way slightly. Right? So that's the Lagrangian. The Lagrangian gradient must be equal to 0, gradient with respect to x only, at the solution x star lambda star. These sets of conditions basically say your x star must satisfy all the constraints that were required. Right, so all the equality and inequality constraints must be satisfied. So with the negative sign in the definition of the Lagrangian, these Lagrange multipliers will always be non-negative. So that sign choice there is to make this lambda greater or equal to 0 as opposed to lambda less than 0, right? So this author prefers lambdas to be positive at the solution. And this last condition basically says, it's called the complementarity condition. Either the constraint is satisfied, well, it's not either or. It's lambda is equal to 0 or the constraint is satisfied. You might have both become 0. So you might have lambda equals 0 and constraint equals 0 simultaneously. In those cases, so theoretically there is no problem having that situation. But those are usually the cases where your constraint is not well defined in the sense that you have some kind of redundancy, which then creates this situation. So something like x squared equals 1 and x to the power 4 equals 1 are essentially the same constraint. X equals, absolute value of x equals 1 is also the same constraint. So so if you have, instead of using x squared, x transpose x minus 1 equals 0, or let's say x transpose x minus 1, let's say greater or equal to 0. Instead of that, if you do something like, that's not good. Trying to think of an example. Yeah, I think it's more like something like this would probably be a better example. So if you have an expression for the constraint for which the gradient of the constraint contains a function times another function, which could have been a simpler constraint essentially, like x transpose x less than equal to 1 could be an equivalent constraint here. This kind of situation happens. The practical implication of this is typically a slower convergence. So typically you want to simplify your constraints. There are several sets of checks. For example, this book starts by talking about linear independence of gradients. Let me see. LICQ. Constraint qualifications. Yeah. I think I missed it. Oh, here. Okay, there. It's at the top. Anyway, so it's called LICQ, for Linear Independence Constraint Qualification. So basically, if your constraints are expressed in a way that satisfies one of these constraint qualification definitions, then you have theorems that guarantee that nice things will happen. And if you don't, you can expect some poor convergence here. So it's just a matter of optimization speed mostly. So no need to worry about those. So back to these. If I relate to this lambda is not that lambda, of course. Lambda is our parameter x. So we need to make sure that whatever lambda we choose makes the Lagrangian equal to 0. And also satisfies the constraint at the solution, right? So typically, for inequality constraint problems like this one, people do the following. Let's assume this constraint is not here. Solve the original problem as if it is unconstrained, and see what we get for lambda, right? And then check if that solution, lambda star, satisfies the constraint. If it satisfies the constraint, then we're done. If it doesn't satisfy the constraint, then we just found out that we cannot ignore the constraint. So we actually have to solve it properly, taking the constraint into account. And the reason of that procedure being reasonable is the following. These Lagrange multipliers split the constraints into two sets. I mentioned active and inactive sets of constraints earlier, but didn't specify exactly what they were mathematically, right? So the constraints that are satisfied as equalities, so all the equality constraints, and these inequality constraints which end up having a lambda equal to 0. So those are called active constraints, and that means they're actively blocking us from moving to further reduce the function objective. The inequality constraints where the lambda is 0, I hope I didn't say it wrong earlier. So the inequality constraints for which the Lagrange multipliers end up being 0, we call them inactive constraints, which means they're not in our way to reduce the function value further, right? I think I remember giving an example like, suppose you're trying to minimize a function which might have equal contours like this. And our inequality constraints might be like, you need to be on this side of that line, and you need to be on this side of this other line. So those are two inequality constraints that are linear. So I need to stay in this shaded area here while trying to go downhill towards this point, right? So here, the optimal solution that satisfies the constraint will be probably a point around here, right? Where this constraint is actively in our way, blocking us from going down further. Whereas this other constraint here, that's not bothering us, right? Its location is not a constraint for our local movements. So the lambda for inactive constraints, Lagrange multiplier will be 0, indicating that the location of this is not, our function value is not sensitive to the location of this boundary. and this one will have a lambda that's strictly greater than 0, indicating that if this boundary was slightly pushed away, then we would reduce the function value at this rate. Okay, and there's a derivation for that later here if you're interested in checking it out. Yeah, so here, oops. Yeah, basically, this derivation here says that epsilon is a small perturbation to the location of this constraint. So the value of our function is going to go down at a rate proportional to negative lambda for that constraint, right? So large lambda for a constraint means that if you just move that constraint slightly away, you could have a huge gain potentially in terms of function value reduction. So before we turn back to our original problem, the implication of that is the following. So typically we have constraints like, let me just say x transpose x again as, okay, I'll just use c of x. So we might have a constraint like c of x must be less than or equal to some threshold. And in many cases, this threshold may not be a hard constraint. It's something that you thought was a reasonable value, right? So if you solve your problem with your selected gamma 1 value, so equivalent constraint here is c of x minus gamma 1 negative greater than or equal to 0, right? So that's in standard form now. So if you solve the constraint for this value of the threshold, which means your threshold is here, your constraint boundary is here. If the lambda corresponding to this, let's say you get lambda 1, turns out to be really large, then you might reconsider the value of this threshold here, right? If you were not, if this choice was not a matter of life and death, right? If you push this value slightly to this direction, if things will not explode, if people will not die, right? So you might say, maybe I'll just change this value a little and benefit from, reduction in the function value at this rate. So so it can actually guide you to redesign your constraints if those constraints were not actually crucially dependent on those values. Okay, so so because of this observation that some I lost so many things. Okay, here. So because of this observation that at the end some of the constraints will be inactive and some will be active. Typically a small number of constraints ends up being active, and most if you have too many constraints, most of them end up being inactive typically. Basically, I might try my chance and see if the constraint I have is relevant or not, right? So in this case, let's say I'm trying to minimize this function here, right? So I'm trying to get to that point here by minimizing this f. And let's say I have an inequality constraint that says I must stay on this upper side of this line, right? So you can see that I could start here, move downhill, come over here. At this point, the gradient became 0. I reached the unconstrained minimizer. This constraint never bothered me. It's at this completely irrelevant location, right? So this is an inactive constraint for this problem. So I might as well ignore it and just solve the unconstrained problem, right? And that's what we will do here. So let's assume that constraint will be inactive. go for the unconstrained solution, and then check if we satisfy the constraint or not. If the constraint was active, right, in this case, let's say the constraint was here, so I need to be above this. So I ignore the constraint, I go down to the unconstrained minimizer, and then I have to go back and check if I satisfy the constraint at this location, and the answer is no. So my ignorance here does not get me to an acceptable solution, so I have to actually solve it properly as a constraint problem. Okay, so that's so it turns out in this case, when we drive the EM algorithm for Gaussian mixtures, this procedure of ignoring the constraint and then checking afterwards will work fine. So we'll be able to solve these as unconstrained problems. But in general, that's not possible. Okay, so let's do some derivation here. I'm going to just mute this screen here. Okay, so I'm hoping that this lambda greater than or equal to 0 constraint is inactive, which means I can simply check the value of lambda, find the value of lambda that makes the gradient equal to 0, and then I'll check if the constraint is satisfied. So my derivative at the, this is actually a scalar lambda, so the gradient is a scalar derivative of summation I log p ki lambda. Right, so at the solution, I'm hoping that, so I'm going to call this tilde. That's a candidate solution. Once I solve for this and verify that the constraint is satisfied, I'm going to declare it as my ML solution. Okay, so let's plug in here the expression for the Poisson distribution, lambda ki factorial, right? So I'm going to evaluate the Poisson PDF at every value of ki from I equals 1 to n, for I equals 1 to n, and then equate to 0. So before we proceed, let's just do some simplification. So here we have negative lambda plus ki log lambda minus log ki factorial, right? So that's my log PDF here. So I can switch the order of differentiation and summation. So I'm going to have a summation and the derivative of these. So derivative of negative lambda with respect to lambda is negative 1 plus ki derivative of log lambda is 1 over lambda, and this term doesn't have any lambda, so it's a constant relative to lambda, right? So we have 0. So that's the derivative, and I'm going to evaluate at this unconstrained minimizer candidate. So if I do some cleanup here, this is 0 equals negative n summation of ki's plus 1 over lambda at lambda tilde ml, which is my candidate for now, summation ki, okay, and then from here you can see that we can move things around and get lambda tilde ml is 1 over n times, okay, so it's a sample average, and I need to check my constraint to make sure that this is greater than or equal to 0. All these ki's are greater or equal to 0. So when I take a sample average, this will be satisfied. So I can, now that I know this unconstrained minimizer maximizer satisfies the constraint, I'm going to declare it as my lambda hat ml. So lambda hat ml is 1 over n and k. Well, technically I also need to check the second order derivative to make sure it's negative, because we're maximizing. So you would need to take the derivative of this with respect to lambda, which is the second derivative, and then plug in this expression to see if it's negative, right? So that should be the case. Okay, so we ended up getting sample average again as our maximum likelihood estimator for the mean. So because this is a random quantity, you can take the expected value of this variance. It's going to depend on lambda. So expected value of this will be lambda, because it's going to be 1 over n times n times lambda. So n's will cancel. Variance of this will be lambda over n. Right, so lambda. This is similar to what we had yesterday for the Gaussian case. It's an unbiased estimator, right, for every n. And asymptotically, as number of samples go to infinity, the variance will go to 0. So it's a consistent estimator. So when is a case, then yesterday I was saying sample average may not always be a good estimator for the mean parameter, the center parameter. Right? So if the variance, remember in this case lambda is also the variance. So the variance of the sample average ends up being variance of the random variable divided by n. Right? So if this variance is infinity, then you can divide it by any n you like. It's not going to go to 0. Right? So your variance of the estimator will be infinity of your sample average. So same thing with the Gaussian. We had sigma over n. If sigma had infinite eigenvalues, I mean, for a Gaussian you won't have that, but if the variance of the random variable in that case also was infinite, then sample average would not work. Do you know of any PDFs that have an infinite variance? It's a really weird concept. So you can check the Cauchy distribution. So the variance of this PDF is infinity. There's a general class of distributions. They're called alpha stable distributions. Most of these, Cauchy is a special case of it. Most of these have infinite variances. Actually, for most of these, we don't even have an analytical expression for the PDF, so you couldn't even begin to compute the variance. So the statistics of these, so these PDFs are not actually described in terms of PDFs as a function of random vector x, variable x, but rather they're described in terms of the characteristic functions, the moment generating functions, which I'm sure you have seen in probability theory. But anyway, so we don't need to go there. So if you have these kinds of situations, then in order to estimate parameters like mean, in these cases those are called centrality parameters, because mean doesn't make sense. It's also not computable. The integrals just don't converge. So the general name is centrality parameter to indicate where the PDF is located along the axis, let's say, if it's one-dimensional. So to estimate those, so we resort to techniques called robust, from robust estimation. So there's a dedicated subfield specifically to estimate parameters in the cases where sample averages don't work. So these are useful for modeling situations where you might have data that has lots of outliers. So these are usually heavy tail distributions. Their tails have lots of probability density extending for long distances away from the center. So they're good for modeling cases where there are lots of outliers, or some outliers. Okay. So let's now put a prior on lambda and solve for the map estimate. Okay. So I don't remember the expression for the gamma PDF, so you'll have to check. Don't use Wikipedia for your actual work, though, right? Because it might have mistakes. Okay, so here's the PDF. I'll use the version here with alpha and beta as the parameters. Well, you don't see it, but I'm just going to write here. So the gamma PDF will be used as a prior for that lambda parameter, and the gamma PDF is so it's beta to power alpha, gamma function x alpha minus 1. This is lambda, and e negative beta. Okay, so that's my prior. Okay. So now I want to upgrade my estimator from maximum likelihood to map by assuming a certain prior PDF for it. So I still need to pick alpha and beta. Right, so yesterday we assumed a Gaussian prior for the mean mu, and that prior had parameters m, c that I had to choose. So there are procedures for selecting those. For now, let's assume you magically know that some particular alpha beta pair is a great match for your situation. So my map estimator will maximize the same thing, right? So I'm gonna start from here. So this is log likelihood plus log prior. So plus log prior, which is that PDF. Sorry. Okay, so again, let's plug in here. Log prior is okay. So negative lambda plus ki log lambda minus log ki factorial. Okay, so that's what we have here. And again, of course, I have the constraint, so I'm gonna maximize this subject to the constraint that lambda is non-negative. So we'll do the same thing. We'll ignore the constraint, assume it's going to be inactive, and we'll go for the unconstrained maximizer by taking the derivative, equating to 0, and then hope that the unconstrained maximizer is going to satisfy this. Okay. So so 0 equals derivative of this, which we found earlier as, I'm just going to write it as, again, negative 1 plus ki over lambda. Okay. So derivative of log that, I'm just going to write it explicitly first. So log of that expression is, there is no lambda here, so I'm just going to leave it as a log whatever, constant. And log of lambda to power alpha minus 1 is alpha minus 1 log lambda. Oh no, I'm not going to take the derivative yet, sorry. So, log. Am I taking the derivative? Oh yeah, I'm just taking the log, not the derivative. Log lambda, and then minus beta lambda. Okay, so we're going to take the derivative. The first term doesn't have any lambda in it, so it's a 0. So we have here negative n plus 1 over lambda summation of the samples, right? And 0 alpha minus 1 divided by lambda, similar to this term here, and minus beta. So at the map estimate, hopefully, will satisfy the constraint. Let's see. So if I move these negative n, negative beta terms to the left, so I have n plus beta equals 1 over lambda alpha minus 1 plus the samples. Okay. So from here I get lambda equals this bracket divided by n plus beta. Right, so from here lambda equals, so at the root is alpha minus 1 plus summation of my samples divided by n plus beta. So make sure you check the math so that we don't have any sign mistakes or something. And that looks right to me, so I think it's fine. I need to check that this satisfies the constraint, then if it does, I'll be done, right? So is this greater or equal to 0? The samples are non-negative, so this summation of samples is greater or equal to 0. In the gamma PDF, there are some constraints on the parameters, so let me just write them. So these alpha and beta must be both greater than 0 for that to be a legitimate PDF. So since beta is greater than 0 by requirement there, right? So n plus beta is greater than 0, so there is no sign change due to this division. The summation is non-negative, so we're good there. If alpha is greater than 1, then we are certain that this is greater than or equal to 0, so we're done. So for alpha greater than 1, we satisfy the constraint. If alpha is between 0 and 1, which is allowed, it depends on the samples. Right? So if the samples end up adding up to more than alpha minus 1, then we're good. If not, then the constraint is violated. So this is not the solution to the constraint problem. We need to solve it properly using constraint optimization techniques. Okay, so so I think in practice, typically your samples will add up to sufficiently large values. Right? I mean, if you have if alpha is between 0 and 1, then alpha minus 1 is between negative 1 and 0. If you have a single k, which is 1, right, a single k, then you end up overcoming that negative value to begin, right? So in practice, with a single sample, and if the true lambda is greater than 0, right, with a single sample that's 1, you'll have this work out. Okay, so what happens here? So now I'm going to declare this as my map solution. Now that I know it satisfies the constraint. So how is it different compared to the ML estimator? You can see that the parameters of the prior, alpha and beta, appear here in the numerator and the denominator. So there is some regularization effect here. As they say, the the estimator is biased by the presence of the prior. Right? It's biased because this was unbiased. This is now a biased estimator. On average, it's not going to be equal to lambda. You can check it out. And how much bias you introduce depends on the value of alpha and beta that you choose for the prior. So you can play with different alpha beta values to see. You can figure out what the bias is and see what happens. Okay, so we introduced bias. So specifically, expected value of lambda hat map is this is a constant. So this is n times lambda. Right? Is equal to alpha minus 1 over n plus beta plus n times lambda over n plus beta. So I think it's, if I'm doing it right, the expected value is equal to this. So as n goes to infinity, as number of samples go to infinity, the numerator and denominator both increase linearly with n. So we approach, so n dominates the denominator, and lambda n dominates the numerator. So this approaches lambda, which is the true value. Right? So it's asymptotically unbiased, which we expect because if you recall, as number of samples go to infinity, the map estimator converges to the ML estimator. Right? And then ML estimator is unbiased, so it will become asymptotically unbiased. So why would you add this bias? Right? Not for no reason. If you look at the variance, right, so the variance of this, what is the variance? So if I split it into a constant plus summation of samples divided by that, it's going to be 0 variance for the constant, 1 over n plus b beta squared. Variance of the sum is sum of the variances. So that's n times lambda. So that's the variance of this estimator. Right? What's the variance of the ML estimator? It's lambda over n. So depending on the value of beta, right, the variance could be significantly smaller or close to lambda over n. If you choose beta close to 0, then these two variances are close to each other. But if you choose beta to be large, then the variance of the map estimator can be smaller significantly. Right? So you're going to accept this additional bias here. So there's added bias here. But we have reduced variance, right, in return. Right? So that's a trade-off you have to make, and that's why they call this a regularization term. You're accepting some additional systematic error in exchange for reduced variability from one sample, one data set to the next data set. So you have a more consistent behavior, let's say, each time you apply this on different instances. Right? So this is called bias variance trade-off. The same thing happens with the Gaussian case, with the prior and without the prior. Okay. So you keep hearing this bias variance trade-off phrase in machine learning or in statistics in general, and the idea is you will add some kind of prior knowledge to the estimation process, but of course that prior knowledge is not informed by data. It's your a priori expectation of what these parameters should look like, right? What type of values they should potentially take. And when you do map estimation, you're augmenting your prior knowledge or assumption about the model parameters with actual data, right? So you're incorporating evidence into your prior belief, and as you add more and more data, your prior belief is irrelevant. You will go to a completely data-driven estimator, which is nice. But when you have limited amounts of data, if your prior is selected well, you might end up having a great bias variance trade-off, right? So you add some error systematically on purpose, but hopefully with limited data, you can get a good low variance for your model. Okay, so this kind of added term, as I mentioned, so for map here, this second term that we added, plus log prior, that's typically called a regularization term. Okay, so regularizer, and this is your data quality of fit to data. So the first term, the likelihood part, measures how well your model fits the data, right? And the second part regularizes the model.
Can you say what the first part is?
I mean, it's called quality of fit, expected loss. I mean, it has various names. So each of the names make sense in some different contexts. But in general, I think quality of fit to data is a nice phrase that captures this term. So typically, optimization objectives in machine learning will have these two terms, and this is the historical reason for it, right? So so you'll have a quality of fit measurement that looks at how well your model expresses the data, and you'll have a second term which basically tries to keep your model parameters under control, in some sense. Okay, so we have 30 minutes. I think we can now go to line fitting with least squares and motivate it as a maximum likelihood procedure. Okay, so we're looking at this linear least squares as ML estimation. Okay. So I'm going to assume that I have a data set which consists of x-y pairs, where xi's are vectors, yi's are scalars. Okay, so we have n samples here. Let's say n samples, and let's say these are IID. So xi is small n dimensional, y's are scalars, and I'm assuming that these are generated according to the following model. So y is equal to let's use w transpose x plus I'm going to use v, so I'm going to use n. No, I'm using n for samples, so yeah, let's use u. Okay, so w is a vector that defines a linear relationship between x and y, and u is just additive Gaussian noise, right? So u is Gaussian with zero mean and some variance. X, I'm going to assume x also to be Gaussian with some, let's say, zero mean and covariance matrix sigma. Okay, so because x is zero mean, W transpose x is zero mean. It's actually Gaussian distributed. X and u are independent. So I add two independent Gaussians. The sum is Gaussian distributed, and its mean is 0 plus 0, so that's 0. And the variance of y is W transpose sigma W plus sigma u squared, right? So as a result, y is a scalar Gaussian with zero mean and W transpose sigma W plus sigma u squared. That's the variance. Okay. So in fact, x and y together, if I stack y into the same vector as x, the xy joint vector is a multivariate Gaussian itself, right? So So before we proceed, let's look at what happens to the joint of xy. So joint PDF of xy is equal to, because we'll need it, right? Because that's a vector combining both x and y. So I need the joint likelihood. So from Bayes' rule, the joint of xy is conditional of y given x, right, times the marginal of x. Okay, and these are both Gaussians. Right, so what is the PDF of y given x? It's a Gaussian. What is the mean value? If I tell you the value of x, you know the value of w. So w transpose x is a known quantity now, right? It's a known value, and that's the mean value of y. So the mean of y conditioned on x is w transpose x. What is the variance of y given x? Well, since this is a constant that's known and it's the mean, all the variance is due to u being added. So it's sigma u squared. I just want to point out the difference of distributions for y with no condition, right, which is zero mean and whatever variance, versus y conditioned on x. So as soon as you know the value of x, the value of y conditioned on that value is different, obviously. Right? So that's it. And distribution of x is this Gaussian with zero mean sigma covariance. Right? And yeah, so this is basically, the first one is basically the noise distribution shifted from zero mean to W transpose x. Right? The variance stays the same. Right? So here is a random variable. We add a deterministic constant to it. It changes the mean, not the variance. Right? So this is the measurement noise distribution shifted to a new location. Okay, so my task is to find the maximum likelihood estimator for W. Let's call this true one W star. So W star is true to discriminate between all these W's. My goal is to find a maximum likelihood estimate for this true W vector. And I have here n samples independently generated according to this process. So they're identical distributed and independent as well. So let's write out my maximum likelihood estimator will maximize, right? So among all the W's that I could choose, I'm going to choose the one that maximizes log likelihood of x1, y1 to xn, yn, all of these, right? And W is a parameter. Okay. So since these are IID, the joint likelihood of the entire data set breaks into a product of, right? So this is log product likelihood of a single data vector, right? So in this case, my data vector is xi, yi combined, and now I know the joint of xy given the, actually I should put here given W because it's a parameter. So given W, so here given x and W, and here it's x given W, but x given W, x does not depend on W, so I can drop that condition, right? So P of x given W is the same as P of x, since W has nothing to do with x. Okay, so I'm going to plug in this PDF here. So first I'll make this a summation. And then I'll break this as P of yi given xi w times p of xi given w, but x is independent from w, so x condition on w is the same as x, has the same PDF as x. Okay, so let's do some substitutions. Since the conditional xi given w simplified to likelihood of xi without any dependence on w, when you maximize this expression here, right, so I'm going to maximize this with respect to w. This second term here does not depend on w, so I can just drop it. It's an additive constant, right? So you can drop it. So we're down to this conditional PDF, which is this Gaussian with a mean W transpose X and variance sigma U squared. So since my so this is a Gaussian PDF with W transpose Xi as the mean, sigma U squared as the variance. Okay, so let's plug that in. So summation log. Okay, so y is a scalar. So this is a Gaussian for a scalar random variable. Dimensionality is 1. So 2 pi negative 1 over 2. Determinant, sorry, there's only one variance. So determinant is just sigma u squared. Squared to power negative 1 over 2. That's the normalization constant, right? And e to the power negative, actually it's scalar, so I'm going to just write it as negative yi minus the mean, which is W transpose Xi squared divided by 2 variance. Okay. So this is e to the power negative. In the numerator I have y minus mean squared, and denominator is 2 times standard deviation squared. Okay, so this log 2 pi whatever, log sigma u whatever, these things don't have any w in them, so I can just drop them, right? So this is equal to, those are additive constants that don't depend on w, so we'll be down to log of this exponential, which is negative 1 over 2, and that's a constant which doesn't depend on I, so I'm going to take it out. Negative 1 over 2 sigma u squared. Okay. yi W transpose Xi squared. Okay. So we're going to maximize this. Now you can see we have the sum of squared errors. Okay. So I can equivalently, I can minimize, I can multiply this with negative 2 sigma squared, 2 sigma u squared. So it's going to flip the objective, so I'm going to minimize. Then I can divide by n. So this is equivalent to minimizing 1 over n summation of squared errors. Right. So that's mean squared error estimated with a sample average for the mean. Right. So that's your linear least squares model fitting procedure problem derived starting from maximum likelihood with Gaussian distributions. Okay. And well, so you know how to solve the rest. Yes.
Why did you switch from argument to argument again?
So I multiplied with y is philosophical, I guess. So I'm going to multiply this with negative 2 sigma u squared over capital N. And that's a negative number, so maximization will become minimization of this flipped function. And my goal here is to end up with a linear model that appears in a least squares problem. So this is minimization of squared error. So this is your usual linear least squares. You know, best line fit. Maybe that's what you called it. So, okay. So if you're, remember what the model was. The model was my y value is a linear function of x plus Gaussian noise. So there's additive Gaussian noise here. And there's a linear model here. Okay. So, and the assumptions we made here are u is Gaussian, x is Gaussian, whatever, and u, x are independent, and x and w are independent. So those are the things we assumed. So this last one is, if w is a fixed parameter, then we cannot talk about statistical independence because it's an unknown deterministic quantity. Then it's just a parameter. But when we add a prior for w, then we're starting to treat w as a random vector itself. So in that case, we need to make this assumption that the parameters are drawn independently from the x values. Right? So under all these assumptions, maximum likelihood estimate of w is the minimum squared error, mean squared error estimate of w. So they're identical. So if your additive Gaussian noise here, is not Gaussian, so you look at your problem and you realize that y might be linearly related to x, but there's an additive noise that's probably not Gaussian distributed. So what does that mean? And if you like maximum likelihood, and remember we like maximum likelihood, it has really nice properties, then you should not use least squares. For example, if your additive noise was Laplacian distributed, so Laplacian distribution is exponential decay. Some constant. Okay. So if your additive noise had this exponential decay type PDF, this is called the Laplacian PDF. It's not e to the power quadratic anymore. It's e to the power first order polynomial. Right. So what would happen is if you go through the same exercise, instead of this e to the power negative y minus w transpose x squared, you would have the absolute value. You would have here absolute value, no square, absolute value, right? And then that would come here as absolute value. So if your additive noise is better modeled as Laplacian, then you should be minimizing mean absolute error. Right? So it's the absolute value of the error as opposed to error squared. If you think your noise is coming from a generalized Gaussian family with a e to the power, let's say, u to power 4, so this is a fourth order generalized Gaussian PDF with some more details, right? Some parameters around. Then this will be to power 4. So the squared error choice in the context of maximum likelihood parameter estimation is specifically tied to making this Gaussian additive noise assumption. And if your additive noise is not modeled well with a Gaussian, then you should not use least squares. So, for example, if this additive noise was Cauchy distributed, right? Remember, it has infinite variance. This whole process doesn't make any sense because, so if you did least squares here, and the u distribution was actually Cauchy, then all of these quantities actually have infinite variance. You add them up, this has infinite variance. The objective on average is infinite. So you could not even start to minimize it. So that's why you need to resort to those robust estimation techniques. Okay, so when I'm doing some curve fitting, I'm always thinking what my model is. Right, so do I have a linear model, a nonlinear model between x and y? And do I have additive noise? If it's additive noise, then what's the distribution of it? So once you make those choices, you can do maximum likelihood estimation, and everything will just fall off nicely. So you just follow the math. So let's now go to quickly generalized linear models. So we'll replace this with a linear in parameters type model. Okay, and everything will be the same. So suppose your model is now I actually prefer calling these linear in parameters. So you can see both of these phrases. So your model for y is this. So instead of W transpose X, we have W transpose B1X, B2X, whatever, BMX. So I choose some nonlinear basis functions. These could be polynomials of X. They could be other basis functions that you like. So you choose your nonlinear functions, B1, B2, B3, etc. And you try to express y as a linear combination of x passed through each of those nonlinear basis functions. Right, so overall, the model is nonlinear in x, but relative to w, it's linear in the w's. Right? So all I have to do is, if this is Gaussian again, if u is Gaussian, x could have whatever distribution, I don't care, because see here, the distribution of x is irrelevant, right? That's going to not depend on w, so it's going to drop off anyway. So x has some distribution. And all I need is u is independent of x in each sample. And I also need w to be independent of x. Right? So if I'm going to put a prior on w to regularize it. So all I have to do is replace this. Every time I see W transpose X, I just need to substitute W transpose times this BX vector. Right, so here. So if you go through that, this becomes YI minus W transpose B XI, right, so squared. So I will take sample XI, pass it through each of these functions, B1, B2, B3. So I'm going to get this B vector valued function, evaluated at xi, multiplied with W transpose. That's my mean value for this Gaussian here. Yeah. So this given xi is now dependent on B of xi. So you get a nonlinear least squares fit. Now it's nonlinear model. A nonlinear model optimized to minimize the squared error. Okay. So tomorrow I'll just show an example where these are polynomials of x. So we can do polynomial fitting. So if you regularize the w by choosing a prior for w, what happens? So let's look at that case. So now I want to minimize. I want to have a prior for w, which is. So I have a PDF for W which is Gaussian. Let me actually just write here. I'm going to assume a Gaussian prior which has mean M, covariance C, like before. Okay. So W is a vector which I assume is drawn from this Gaussian PDF. And then for each sample pair xy, yi, I draw a sample of xi from its PDF, a sample of ui from its own PDF, pass x through the model that uses parameter w, and so let's look at the linear model. And then xi is drawn from whatever PDF, I don't care. And yeah, that's it. And xi's are, so everything is independent. Okay, so I have my log likelihood portion here simplified already, so let's take that. So my map estimate will maximize log P of my data plus log P of W, right? So log likelihood of my data, it's already simplified here, so let's just copy that. So it's equal to maximizing minus 1 over 2 sigma squared yi transpose xi. Okay, so the plus log prior part is so that I'm just going to write the expression for this Gaussian. So 2 pi. So these are n-dimensional vectors, w's and x values. So n over 2 c negative 1 over 2 okay, a little squeezed here, but okay, so that's my Gaussian for W. So it's a log something with 2 pi, something with c, determinant of c, e to the power, the usual quadratic. So that's a plus log 2 pi stuff is constant, c terms with c are constant. So I'm just going to have log negative 1 over 2, that exponent here, right? So I can just write here minus 1 over 2 w minus m transpose c inverse w minus m, right? So this plus that term. So if I multiply this with a negative, so like there, multiply with negative 2 sigma u squared over n. Yeah. Then I'm going to be minimizing 1 over n. So I'll have my average squared error term like before. And so this negative 2 cancels negative 1 over 2. We have plus sigma u squared over n. Yeah. Okay. So the prior appears here. So that's the solution to that is my map estimator, right? So this first term is quadratic in W plus another quadratic term in W. So this is quadratic in W. There are no constraints on W, so I could take the gradient with respect to W. It's going to be a linear function of W, equate to 0, right? So I'll solve that linear system, and I'll get my map estimator. So let's do that. Okay, so I'm going to write this expression here in matrix vector form as follows. So I want to define this capital vector X, which has x1, x2, xn in columns. I think I did something similar in the solutions that I sent out. So I'm going to define this vector y, which has scalars y1, y2, yn in the vectors. So then this problem becomes like so. Mean. Okay, so I have 1 over n. So this summation becomes y minus xw. I think I could just get rid of n. Y minus x is capital XW transpose y minus capital XW plus sigma u squared over n w minus m transpose c inverse w minus m. Okay, so that's my objective here, right? So this is what you're used to seeing normally in least squares, right? So the model here is that some matrix x times a small vector w will give me this this other vector y, and I have more values in y than number of entries in w. So I'm trying to find an approximately squares fit. Okay, so let's take the derivative equate to 0. Actually, I'm just going to ignore this division by n, so we have less clutter. So 0 is equal to, okay, so the derivative of this with respect to x is 2 times y minus x w transpose x, and there's a negative. I'm hoping I'm doing this right. Transpose is going to be x transpose. Yeah, I think it's right. Okay, and plus it's going to be 2 sigma u squared c inverse w minus m. I think that's it. I just need to transpose this to make them add up. So this will be the column vector negative 2 x transpose y minus xw plus 2 sigma u squared c inverse. Okay, I hope I did it right. Now it's going to be, so let's get rid of the 2. It multiplies everything. So here we have x negative x transpose. Okay, so I'll just write this first. So it's going to be x transpose xw. Negatives cancel, minus x transpose y. I think I have a mistake. The dimensions here didn't work out. Oh, because I have a mistake from all the way. This should have been x transpose. Yeah. Should have been x transpose, and this should have been x transpose. So then this would be x transpose x transpose. Okay, so now they can multiply each other. Okay, so x transpose w, xy, just xy, and plus sigma u squared c inverse w minus sigma u squared c inverse m. Alright, so if we bring together the x term, the w terms, right? So let's bring the w, keep w terms on the right side, and take those terms without w to the left side. So we have x transpose plus sigma u squared c inverse w equals xy plus sigma u squared c inverse m. Okay, so you can see that the solution of the regular least squares problem without the prior would have been x transpose, so this is the maximum likelihood solution, x transpose w equals xy. So that would have been the maximum likelihood solution. So now the prior came in, And it's telling us that the W vector should be close to M. And how close? That's controlled by C. Right? So it depends on the eigenvalues, eigenvectors of C. So we end up having these terms that depend on C inverse and M. So the C inverse is the precision matrix, remember? So C inverse is a measure of how precise your M is as a prior estimate for W. The more precise it is, the more impact it will have here on this matrix and on that matrix, right? So you solve that linear system, you get your map estimate. You can see that as C, as the eigenvalues of C go towards 0, eigenvalues of C inverse go towards infinity, right? So C inverse terms dominate these sums, right? So then data becomes irrelevant because your prior is super confident in this value M. So you'll end up getting M. W map equals M. As eigenvalues of C go towards 0, W hat map goes to M. As eigenvalues of C go towards infinity, then C inverse eigenvalues go towards 0. So now these C inverse terms go towards 0, and you're converging towards the maximum likelihood estimate, right? So eigenvalues of C going to infinity means I think W should be close to M, but I'm really not that certain anyway. So just ignore it if you can. Right? So then it does exactly that. Okay, so let's stop here, and tomorrow we'll see some code examples.